Hello everyone. So I'm going to talk about damping and scaling models for elastic response spectra. This was one of the tasks of NGAVIS2, and you see the working group members on the bottom. So many thanks to Dr. Buzorgnia, Professor Idris, Abrahamson, Campbell, and Dr. Silva. I do want to mention this before I start the presentation, that our goal in this task was to develop a new model to adjust the elastic response spectra for 5% damping ratio to any other damping ratios. But the model that we have developed is not limited for use by the MGA models. It can be used for any GMPE. So here you see the outline of today's presentation. First, I give you a very brief background on the project, and I go over the database of ground motions that we selected to develop our model. I go over the model development procedure for the average horizontal component and show you the proposed model for the median DSF. So the DSF stands for the damping scaling factor that I'm going to use from now on. We also developed a model for the variability of this parameter that I will show you, and then focus on some comparisons with existing models. I will show you how the DSF for vertical component is going to differ from that of the horizontal component, and then close up by listing the products of this project and show you how you can access them. So what was our motivation? GMPEs are typically developed for a 5% damping ratio, but real structures, they can have damping ratios other than 5%. And in this slide, I'm just showing you two examples that are suggesting the different damping ratios for different types of structures and different ground motion levels. On the left-hand side, you see the table from the classic work of Newmark and Hall in 1982. And on the right-hand side, you see a much more recent study that suggests that perhaps for tall structures, damping ratio can be a function of the number of stories. In any case, you can see that damping ratio can change from as low as 5% to as high as 20%, or in some cases, even much higher than 20%. So our goal in this working group was to develop a model for a scaling factor that can be used on the spectral ordinates predicted at a 5% damping ratio by any GMPE to spectral ordinates at any other damping ratio. We were interested in damping ratios between 0.5 to 30%, and we defined the damping scaling factor as the ratio between the pseudo-spectral acceleration at any beta damping ratio to that of 5% damping ratio. Our goal was to come up with a model that can describe this DSF as a function of various predictor variables, damping ratio, spectral period, or any other earthquake and site characteristic that can influence the DSF significantly. The B here is a vector of regression coefficients and some error term that's normally distributed with a standard deviation sigma. So we wanted to answer some specific questions. First, what is the distribution of DSF? What should our predictor variables be? And what should this functional form be? We also looked into the form of the variability of DSF. To answer these questions, we did a comprehensive literature review. You can see the summary of over 25 related studies that go all the way back to the work of Newmark and Hall in our report. We also took advantage of the massive database that Tim has made. So we had over 8,000 recorded motions to look at. This is moderate to large magnitude data. Here you see the summary of our database. So obviously, because our database is limited to shallow crustal earthquakes in active tectonic regions, this is the applicability of our model. We calculated the elastic response spectrum for every single record in our database for both horizontal and vertical components of ground motion. For the horizontal ground motion, we looked into rod D50 and GM rod I50 components, and we calculated the pseudo-spectral acceleration at 11 different damping ratios. They range from 0.5% to 30%. And we calculated this for the 21 NGA periods ranging from 0.01 to 10 seconds. Taking the ratio between the two, we calculated our DSF and ended up with a database of DSF with other parameters. In the graph, you see the distribution of magnitude and distances for the records that we use in our analysis. Now, to actually perform our regression analysis, we limited our data to those with distances less than 50 kilometers. You see the distribution of the magnitude and distance in the figure. For this set of data, our magnitude ranged between 4.2 to 7.9, and we had a wide variety of VS30 as well, from very soft soil to very hard rock, to have a good representation of data. So we developed our model using this data, but then we validated the model afterwards for longer distances by doing residual analysis. For the regression analysis, we ended up with over 2,000 records for the horizontal and for the vertical components. Another parameter that I'm listing here is the duration of motion. I'm showing you the significant duration of motion here, from 5% to 75% of area's intensity. And you can see the range for each parameter. The reason that I'm showing you this is because duration of motion is a very important parameter influencing DSF. So it turns out that distribution of DSF can be approximated as a log normal distribution at a given period and damping ratio. In this slide, you see an example at a 2% damping ratio and 3 different periods, 0.2, 1, and 7.5 seconds. What you see here is the data for natural log of DSF and a fitted normal distribution in red. And on the top, you see the normalized frequency diagram. On the bottom, the empirical CDF. This basically shows that log normal assumption is very reasonable in our study. The next question to answer was, what are the predictor variables? We looked into the literature. Obviously, damping ratio is a necessary parameter that's been used in all models. Period is a common factor in all the existing models. But duration, magnitude, and distance that I'm showing by D, M, and R in this presentation have been considered in very few studies. They are very important parameters, however. 1 or 2 studies look into the effects of side class and tectonic settings as separated by Western US region and Eastern US region. We also looked into our database to find the appropriate predictor variables. We see very systematic patterns with damping ratio and period as expected. In the plot here, you see the median DSF plotted versus the period at different damping ratios, and vice versa, the median DSF plotted versus damping ratio at various periods. So the pattern is as we expected. For example, at very short and very long periods, the DSF approaches unity, which makes physical sense. And you can see that, here we go. You can see that these plots for median DSF, they range from 0.5% damping ratio on the top all the way to 30% damping ratio at the bottom. As I mentioned before, duration is a very important parameter influencing DSF. And here you see an example of the data for DSF plotted versus the duration of motion at 1 second period. I'm showing you 4 sample damping ratios, 2% and 3% representative of damping ratios less than 5% on the top, and 10% and 20% on the bottom. The pattern are opposite as we wanted them to be, and it's very pronounced, especially as you deviate from 5% damping ratio. So you see more pattern at 2% and 20% in this particular figure. Now, inclusion of duration in our model was not practical because the design engineer doesn't have duration as a parameter when they want to select their ground motion. However, duration is highly correlated with magnitude and distance. So we looked into including magnitude and distance in our model and capturing the effects of duration that way. So here you see an example of data that we have. The magnitude influences DSF very significantly. This pattern is consistent among all periods. And here you see the DSF being affected by distance. The pattern is not as much, but it's still significant enough that we decided to include it in the model because it took away some of the dependence on the duration after we did our residual studies, especially at lower damping ratios. So we went through a lot of different functional forms. We considered what was used previously in the literature, and we considered some other forms of models. Here you see our proposed model for the natural log of DSF, which is a function of the damping ratio beta. moment magnitude, and R-rub. R-rub is the closest distance to the ruptured area. And epsilon is the error term. So you see an example plot of this proposed model at magnitude 7 and distance of 10 on the right-hand side of the screen. The regression coefficients B0 to B8 are given in a table dependent on the period. We also developed a model for the logarithmic standard deviation that you see on the bottom. It has two parameters, A0 and A1, and it depends on the damping ratio. An example of the standard deviation is shown on the bottom figure at period of 1 second. So as you expect, the standard deviation is 0 at 5% damping ratio, which is that division by 5 in the formula. And it increases as you deviate from 5% to a maximum of about 0.2. This number is almost consistent in all periods. And that's where the absolute value comes in the formula, because both sides of the plot, less than 5% and greater than 5%, are basically the same function, just opposite directions. So in our report, we give a table, as I'm showing here, for all the regression coefficients, B0 to B8, and A0 and A1, at different periods ranging from 0.01 to 10 seconds. This particular table is for the rod D50 component. We have another table for GM rod I50 component. We also have suggested a simplified model that doesn't have the distance term in it. So one can use that model, but you have to have in mind that you're introducing some dependence on duration. So I'd like to show you an example application. I took a magnitude of 6.7 and distance of 10 kilometers and generated the DSF based on our proposed model for 0.5% damping ratio all the way to 30% damping ratio. Then I applied this model to a GMPE. The GMPE that I selected is the geometric mean of the original NGA relations. And you can see that it has been scaled up to 0.5% damping ratio all the way down to 30% damping ratio. And depending on the period, this scaling can be quite significant. Here you see the standard deviation plotted for the two parameters, period and damping ratio, that it depends on. It is 0 at 5% damping ratio at the bottom, and as you deviate from 5% to 0.5 and 30%, it reaches a maximum of just about 0.2, maybe 0.25 at some given period. It's not a strong function of period if your period is more than 0.1 second. In this slide, I'm showing you the variation of the DSF with magnitude. So I've plotted that for a distance of 10 kilometers for magnitudes of 4.5 to 8, which is the range that we are suggesting for applicability of our model. And you can see that the variation based on magnitude is very dependent on the damping ratio and on the period. And it can be quite significant or not as important, depending where you are on your period damping range. And here you see the variation of DSF with distance. This figure is for magnitude 7, and I've plotted them for 0 kilometer up to 200 kilometer, which is the range that we are suggesting for applicability of our model. Obviously, 0 kilometer is an extrapolation, but I just wanted to throw it in there as the extreme case. And based on residual studies, we are suggesting that the model is good up to 200 kilometer. Again, variation is very dependent on the damping ratio and the period. We did some comparison with existing models. Here, the comparison that you see is with the Newmark and Hall 1982 model. So what I've plotted from top to bottom is for different magnitudes, 5.5, 6.5, and 7.5. On the left-hand side, we have 5 kilometer. On the right-hand side, we have 10 kilometer. So the black lines are our proposed model that are changing for each plot, for each figure. The red lines are Newmark and Hall's that was not a function of magnitude or distance, so they're all the same in the 6 figures. Here you see the comparison between the two, and given the fact that Newmark and Hall only had 28 records from 9 earthquakes, it's quite good comparison, especially for less than 1 second period. We did a lot of other comparisons with existing models that you can find in our peer report. You can refer to it for detail. Here I'm showing similar plots for the model by Idris 93, Abrahamson and Silva 96. And we also did some comparison with the Eurocode. They had a model for DSF, which is more applicable for damping ratios greater than 5%, which is why you see the very sort of good comparison for greater than 5% and not so good for less than that. We also developed a similar model for the vertical component. The functional form is the same as that of the horizontal components, but we have different regression coefficients. So we have a different table for the vertical component that's given in our peer report. The biggest difference between the DSF for the vertical and horizontal component is that the peak for the vertical component happens at a lower period or higher frequency. And it's also more extreme, so it's a bit higher or lower depending on where you are on your damping ratio. In terms of the standard deviation, it's just a bit higher for the vertical component, which we could expect because the horizontal component that we're considering is in an average sense of the two components, bringing down the standard deviation versus vertical, which is just one component. And let me point this out. So even at its worst case scenario, the standard deviation for the vertical component is less than 0.3, which if you compare it to the standard deviation for the GMPE that's going to be scaled, it's very insignificant. And we did some studies on the correlation between the DSF and PSA at various damping ratios. This is all detailed in our peer report, but the point is that the standard deviation of the scale GMP is going to be mainly controlled by the standard deviation of the GMP at 5% and not that much by the DSF. So to close this presentation, these are our products. We have a peer report that's already posted on the peer website. This is the 2012-01 report, and you can access it for free, as Dr. Buzorgnia mentioned. For those of you who don't want to read a long report, we have a condensed study as a conference paper at the Earthquake Engineering World Conference. And we also have an Excel file that's been distributed. You can contact Dr. Buzorgnia or myself. And I also have MATLAB codes for those of you who are MATLAB code lovers. And thank you so much for listening.
Thank you very much, Sana. Very good. On time. That's okay. You keep that on time. That's the great. Questions for Sanas on damping scaling.
Maybe you could explain what the intended use for the greater display of damping ratios is. The spectral response is the maximum response of a single degree of freedom isolator, but a building isn't a single degree of freedom isolator, and if the shaking goes on longer than 20 seconds, you're probably above a magnitude 7 earthquake. So things are degrading and the damping is probably decreasing, and there's much more time for the concrete to spall off and expose the rebar and lead to all kinds of bad things. So I don't see, it seems like the ground motion should not be reflecting the damping ratios if you're going to have a prediction equation.
So just the quickest thing that comes to my mind is, for example, doing PSHA analysis. If you want to do something like that, you have to change the damping of your ground motion. At first, you can have the PSHA for different damping ratios. Also, in practice, as I understand, they are still using approximate methods rather than doing multi-degree of freedom nonlinear analysis. And for that approximation, it is better to use a damping ratio that's more relevant to your structure. There are some studies that suggest, for example, what damping ratio to choose if your structure is expected to go in the nonlinear range. So you wouldn't use 5%. If you want to do the approximate analysis, you use something more appropriate.
So in fundamental way, you are correct. Ground motion doesn't care unless you include solid structure interaction and so on. Ground motion, you record the ground motion. But as you correctly mentioned, responsive spectrum is response of a single degree of freedom damped system. That damped, it means you have to have a damping value. We use 5% as a reference, but suppose your structure is not really 5%, that is very, very likely. We have experimental data, we have ambient vibration data, we have various data, depending on the structure, depending on the level of shaking, lots of factors involved. Damping can be not 5%. Then you have a tool now. You go from 5% to, depending on, if you have a sloshing mode, for example, of liquid storage tanks and so on, damping is low, very low. If you have concrete structure, not much damage, damping can be high or low, depending on various factors. This is going to give you a tool to scale the response spectrum from 5% to 30% or all the way down to 0.5%. More questions for Sanaz? No? From the internet? Okay, very good. One question generically. Thank you very much, Sanaz. I appreciate that.